Welcome to Astronomy on Tap. It's lovely to see you all in person again. After a year we've been online. So great to be back with full steam. Can everyone hear me in the back all right? Yeah, thumbs up? Nice, all right. A couple of housekeeping items before I get into it. First of all, we're now recording our in-person events to post on YouTube. That way we'll end up with a nice collection from the videos we started with the pandemic. So that's one thing. If you come up here and walk around, you might end up on YouTube. So keep that in mind. Is the mic connected? You guys hear me? Okay, no problem. The other housekeeping item was that there's a cable up here charging our laptop. So if you walk by, be sure not to trip. All right, so if this is your first time at Astronomy on Tap, you should know that Astronomy on Tap is a worldwide organization with many, many chapters. It was first started in New York City about a decade ago, I think, and there are chapters in New York, Atlanta, Texas, Chicago, Albuquerque, and here in the Triangle. So this location in the Triangle is the only Astronomy on Tap chapter in North Carolina, and we're really gracious to be here with you tonight with full steam. So our chapter started way back in May 2017 by a postdoc at UNC Chapel Hill named J.J. Hermes. And since then, we've had 29 events, including today, and including the events we did online during the pandemic. And this is some of the pictures we've had over the years. We're brilliant speakers and all the talks they've given. If you want to keep up with us online for our future events, I've listed on the left here our Facebook link, which is how most people seem to keep up with us. Our Twitter, you can follow us on Twitter to get announcements on new events. Our email address, if you want to send us a question, suggest a speaker, something like that. And then lastly, our YouTube. If you Google or search on YouTube Astronomy on Tap Triangle, you'll see all the events we recorded during the pandemic, which is about 6 or 8 lectures, I think. And you'll also see playlists that we've created where we've compiled a number of talks from different Astronomy on Tap satellites for particular subjects. So say you're really interested in black holes, then you can go on and look at our black holes playlist, and you can learn all about them from Astronomy on Tap chapters all over the world. Tonight we have 2 speakers. First we have Reilly Milburn. Reilly is a physics PhD student at UNC Chapel Hill. He's one of the outreach coordinators for our department. His research focuses on young planets and the stars that they orbit, so to understand planet formation processes and planet evolutionary processes. Our other speaker, Reilly also has a BS in physics from Habitable College, physics and astronomy. Our other speaker is Mugdha Polimera. Mugdha is also a UNC physics PhD student, one of the ones in my group, actually. Mugdha studies the coevolution of black holes and what are basically little dwarf galaxies and how that evolves and interacts. Mugdha is the outreach and diversity liaison for our department. She's a plant mom and she's a service dog trainer, as you can see right here in the center of the room, with eyes, ears, nose, and paws. And so tonight the topic is astronomy in film. I'm going to let Mugdha and Reilly take it away. Feel free to listen in, and then after the talk's over, there'll be plenty of time to answer questions and interact with the speakers. Thank you.
Hello. Sound good? Okay. Speak up. All right. Can you hear me? Great. I'll try my best not to shoot you in the eyes with this laser beam, but I'm going to try and use it. So let's get right into it. So we're going to talk about astronomy in film. That is, we're going to talk about movies, we're going to talk about space, and we're going to talk about movies in space. And we're going to see, basically, Mugdha and I put this talk together to sort of dissect how Hollywood deals with astronomy, how it deals with space, and other physics topics. And we're going to see how they get it right, and how they get it, in some ways, fantastically wrong. So, obviously a big motivation for this talk is the stars. The stars, the cosmos, the universe, everything. For as long as humans have been around, they've been fascinated with the stars. For one, the stars are a great tool to us humans. We can use them to navigate. We can also track their motions and determine when seasons change, when we need to harvest, etc. But also they inspire a lot of stories. One popular example in relation to astrology, not astronomy, but the ancient Greeks and the constellations. You know, the ancient Greeks believed that the stars are placed in the heavens in permanence, and studying their motions, you could predict future or learn morals. Basically, storytelling. Whoop, I pushed a button. Are we good? We're good. Storytelling. But that is to say, the stars are fascinating, and they inspire a lot of stories. So it's no surprise that this tradition of storytelling has carried on to today. And so we see hundreds and hundreds and hundreds and hundreds of science fiction movies about space, that go to space, that talk about space, about beings from space, all kinds of stuff. And I love so many of them. I love movies. I watch them all the time. And while I would love to talk about every single movie there ever was about space, unfortunately we don't have time for that in this time window. So Mugdha and I have selected 3 films that sort of cover the history of film from its earliest days to the modern era. Hopefully they're movies that you all know about. Yeah, unfortunately we won't have time to talk about Killer Clowns from Outer Space. But if you want to talk about that one, meet me after. All right, so let's just jump right into it. So the first movie that we're going to talk about is actually one of the earliest films ever. It's called The Trip to the Moon. It's a French silent film from 1902. And it's one of the earliest and most influential films of all time. It's based off of Jules Verne's 1865 novel, From Earth to the Moon. It's a great book, highly recommend. And it was widely popular for its time. Even though it was a French silent film, it was distributed nationwide in the US, had a big turnout, because obviously, one, it was one of the earliest movies, and 2, it's about space, and everybody loves space. Case in point, you wouldn't be here if you didn't think space was cool. So, you might recognize this one if you've ever read, what was it? The Invention of Hugo Cabret, which is in part based off of the filmmaker, George Méliès, or if you're a Smashing Pumpkins fan, there's a music video that basically recreates it. But yeah, so since this is a really old movie, and it's only about 12 minutes long, I'm just gonna really quickly run through the plot. Sorry in advance, there's going to be spoilers, but I think it's useful. So the movie starts out with a bunch of astronomers. These are astronomers. Let's see if we can get the laser pointer. A bunch of astronomers. They kind of look like wizards, which is kind of fun. The movie itself is very theatrical, but I don't know if you can see up here. We can already tell that the astronomers are fascinated with the moon. They've got their telescope pointed at the moon. They've got a diagram here that looks like it's the Earth with the moon orbiting it. If you look over here, they've got a little model. They think the moon is crazy and they want to go visit it. So they devise a plan to visit the moon, and it involves this very rudimentary spacecraft. It looks more like a bullet. I guess the idea is they want to shoot themselves into the moon. And that is confirmed with this shot here, which might be hard to see, but we've got a cannon aimed at the moon. So they're just going to shoot themselves to the moon. Now, what I think is really fun about this shot is you can see in the background we're on like a mountain range. So I guess the idea of the filmmaker was, if we're really high up on Earth, we will be closer to the moon and therefore easier to get there. Problem is, most mountain ranges are on the order of like 5 to 10 miles high, and the moon is like 200,000 miles away. So it's not helping too much, but I like the spirit, I like the idea. And so they shoot themselves to the moon and they get there. And unfortunately, their idea of the scale of the moon wasn't great, but we won't take off too many points, because they did get some craters in there. Although I will say the moon doesn't have a face. I've seen it, it does not. And so they get to the moon and they start exploring, and immediately they find under the surface of the moon, there's this lush lunar landscape. There's waterfalls, there's mushrooms and other vegetation, there's a log in the middle, which tells us maybe there's like trees. And then obviously the centerpiece of the shot. There's a tiny green guy. He looks like maybe a cross between like a lizard and a chicken or something. But basically that is to say, the moon is pretty habitable in this film, as also you can tell by the very interesting garb of our astronomers. They have top hats and umbrellas and no space helmets inside. So, very fun. And then, so the aliens on the planet are not very happy with our visitors, our astronomers, and so they are hostile, they attack them, rightfully probably so. They ended up coming uninvited and murdering a few of them. So I think it's okay for the aliens to be upset about that. The astronomers end up running away. They fall back down to Earth, and they make a monument to them. And that's essentially the end of the movie. I just want to point out again on this one, you can see in the background, we've got I guess the sun. I think that's the Earth. I don't think that's the moon of the moon. At least I don't know of one that exists. So I'm just going to assume that's the Earth. And obviously we've got the craters on the surface of the moon. So that's the movie for the most part. You can find it on YouTube. It's like 12 minutes long. It's fun. I would recommend watching it. But I just wanted to point out some key dates for reference, just to sort of give us an idea of what the contemporary ideas of when the filmmaker was making this, and some key points of reference in astronomy. So obviously, if you recall, in 1902, A Trip to the Moon was released, which is a movie about going to the moon, but it predates flight, which is kind of interesting, because in 1903, the Wright brothers achieved the first flight in Kitty Hawk, North Carolina, which in my opinion is the actual birthplace of aviation. Sorry, Ohio. So I think that's pretty fun. They have a movie about launching themselves out of the Earth's atmosphere before we even flew on Earth. But what's also fun is in 1920, astronomers Harlow Shapley and Heber Curtis debated the scale of the universe. So it was in 1902, 20 years later roughly, we still didn't have a good grasp of basically the scale of our known universe. We weren't sure if the galaxy that we live in was the full extent of the universe, or if there were galaxies elsewhere, and we weren't sure about our position in the galaxy. So I just think that's interesting. And in the debate, Harlow Shapley and Heber Curtis both were wrong. So it just goes to show how well we actually knew about the universe and our place in it at that time, which wasn't very much. But 3 years later, in 1923, Edwin Hubble proved, this is Hubble in this crazy telescope, he proved that there were galaxies outside of our own, and thus the scale of our universe was much larger than we had ever known about. Which I think is fun when you think about it, because there's so many movies today about galaxies far, far away. But back then, this movie about the moon was pretty crazy, and just the difference in scale is very different. And then of course in 1969, we had the first person to land on the moon. We went there, so we know what it's like, and we know that this movie is kind of a bunch of malarkey, but it's fun to watch anyway. We've been there. And so we know most of the stuff on the moon isn't true, especially that the moon is not a hospitable place, but I think we knew that without having to go there. The moon doesn't have a lot of gravity, and as a result doesn't really have an atmosphere. And so the moon experienced extreme temperature changes. Basically, I would not expect life to exist on it, period, but we know that because we've been. But on the light side of the moon, you might experience it to get upwards of like hundreds of degrees Celsius, and on the dark side, it's like negative hundreds of degrees Celsius. But one thing the movie did get right was its craters, but obviously we've known that for a long time because we pointed telescopes at the moon and we can see its craters. Galileo knew there were craters on the moon, which predated 1902 by a long time. Another thing that I think is fun to point out about this movie is the way they get to the moon is not too far off, which we kind of mentioned already. Essentially what they're doing is shooting bullets, which is based off of a combustion reaction. What we've got going on here is Newton's third law. They're shooting a lot of mass down, which forces us up. So I think that's pretty cool, and a movie in 1902 kind of got it a little right. But one major takeaway I think that's fun to point out is that the core tools of astronomy remain relatively the same today. So in the first scene, we saw their telescope, and astronomy basically works off of the same basic principle. We're studying light, and we want to know, basically we're doing science off of things that we can see, and we have a lot of fancy tools that help us do that. But basically, since its origins, we're still using that one basic principle, the electromagnetic spectrum. It gets a little more complicated when you throw in gravitational waves, but I would still say 95% of astronomy is light you can see. And so, if you look, here's me, and I'm using a telescope, a modern telescope that functions identically, for the most part, as the one in the movie. This one has mirrors. But essentially what it's doing is it's looking at light, it focuses it, and then I can see it. This is optical light. But of course, now today, we can see more than just with our eyes because we have learned more about how light works. So we have new fancy tools to allow us to see different parts of the electromagnetic spectrum. So for example, we can see bigger wavelengths than optical using bigger telescopes. These are both radio telescopes. This is at the Very Large Array in New Mexico. It's a 30-meter dish. One of, I think, 27. Yeah. And then we also got the Green Bay Telescope, which is 100 meters of collection area. That can actually fit 2 full football fields. It's pretty crazy. I don't know if you can see it, but I'm really tiny right here if you didn't think I was already tiny. This makes me feel even smaller. And we also have telescopes in space. The atmosphere actually gets in the way of a lot of light, like X-rays. And so putting telescopes in space actually avoids that problem. So we have Hubble, which many people are probably familiar with, which has taken a lot of beautiful photos. It functions from UV to near infrared. This is an X-ray telescope on board the International Space Station called NICER. It's about the size of a mini fridge, and it's zooming around, and it looks in X-rays. And then in December, hopefully, JWST will go up, which is the next big flagship mission from NASA. It's like over $10 billion or something crazy like that. And it's going to work in optical to mid-infrared. And so hopefully it will allow us to see a lot more crazy stuff. This is a picture from Hubble, and we can already see we can see a lot more than they could in 1902 thanks to our innovations. And we know now that there exist galaxies very, very far away. Which brings me to the next movie in our series, Star Wars. I love Star Wars. Star Wars is great. Yeah. I think I don't need to go through the plot of Star Wars like we did for the last one, because I'm hoping most people know what Star Wars is. But Star Wars was created in 1977 by the one and only George Lucas. It is the 5th highest grossing media franchise with an estimated value of over, I think it's over 70 billion at this point. Which is a testament to the popularity of the stars, in my opinion. Everyone loves Star Wars. And what I like about Star Wars as an exoplanet researcher is all of the crazy, diverse worlds that all of the characters go on their adventures in. So in Star Wars we see, planets with dense forests, like on Endor. Or, we see planets with really thick, cloudy atmospheres, like on Bespin. There's stormy ocean worlds where there's no land in sight. You can imagine there's maybe aquatic life under here, perhaps, like on Camino. There are desolate ice worlds where maybe the planet is orbiting really far away from its host star, or at least it's not receiving a lot of light, and so it's very cold. There's hot lava worlds where finding the high ground is necessary for survival. There's desert worlds that even orbit more than one star, which is pretty cool. So when we talk about all of these different exotic planets, what we're talking about is basically exoplanets. And so for people who might not be familiar, I'll define it. What are exoplanets? That's what I study. Exoplanets are just planets outside our solar system. That is to say, they orbit stars that are not our own. And to date, we've confirmed around 4,500 exoplanets existing in more than 3,200 solar systems, all within our galaxy. Now, it's possible there are billions of exoplanets in our galaxy alone. We have yet to find any exoplanets outside our galaxy. But you might be wondering, Reilly, if there's billions of exoplanets in our galaxy, why haven't we found them? We only found 4,000. Well, the reason why is that exoplanets are very difficult to find. They're very hard to find. The reason why is that exoplanets don't shine like stars do, and so we have to think of clever ways to find them. The most popular, or what we call indirect detection methods, and the most popular indirect detection method is the transit method. Essentially what we're doing is we're studying starlight, and we're inferring the existence of planets based on how that brightness changes with time. So this diagram sort of depicts that. Essentially, you can imagine if you have a planet orbiting a star, and that planet passes in front of the star in our line of sight, what's going to happen is that star to us is going to look different because that planet is blocking some of that starlight. And so if we look at a star and we see that brightness go down and go back up and then go down again, and go back up, and this happens periodically, we can then infer the existence of a planet, and we can say to our other astronomy buddies, hey, go look at this, I think there might be a planet there, and they can follow up and confirm it. And so we found the majority of the planets doing this. That's not the only way though, there are a few other methods. For example, we have actually directly imaged planets, though of course we don't get a lot of detail because they're very far away. But this is an example of a solar system that we have directly imaged. I mentioned planets are very hard to find because they don't shine like stars do. So, if you look out in the sky, you see a bunch of stars. I can't just go outside, point, and say, oh, there's a planet there, because they don't shine, or they're outshined by their stars. And that's what's happening here. So basically, this star would normally outshine these planets orbiting it. But we have clever ways of masking out that starlight so that we can then see the planets shining and orbiting around. But again, this is like the most detail that we're going to get of a planet outside of our solar system, because they're just so far away and they're hard to see. But based on our observations and our direct detection methods, we can infer properties of planets, and we've determined, at least I think, that the exoplanet population we found is fairly diverse. Basically, looking at that signature dip in light, we can infer a size based on how much light it blocks out of a planet. And then based on gravitational interactions with the host star, we can infer a mass. With a size and a mass, you can then infer a density. And knowing a density, you can then start to hypothesize what these planets are made of. So for example, if you find a planet that is of this similar density to Earth, you might say, oh, that planet's pretty Earth-like. And if you find a planet that's bigger than Earth, but still kind of like Earth, you might say, oh, that's like a super Earth. Or if you find a planet that's, a similar density to Jupiter, you might say that planet's pretty Jupiter-like. And we've also found planets that are ginormous. We've found planets that are really small, really hot. We've even found planets like in Star Wars that orbit or that are in multiple star systems. This one's in 3 actually, which I think is pretty dang cool. But one problem I got with Star Wars is they never wear any spacesuits. They're running around with their robes and lightsabers. They have no breathing apparatus. They're just out there. So what's the deal? Well, I guess we could say that all of the planets that they visit in Star Wars are habitable. And astronomers, that's something that astronomers are also interested in finding. Can we find planets in our galaxy that are habitable? And that's based around this idea of the habitable zone. So basically, the habitable zone is a theory about where we think we could find life like we have on Earth, based around a very simple principle. Is the planet in a position to receive enough energy such that it has liquid water and its atmosphere is conducive to life like on Earth? And so it's kind of in this Goldilocks zone. But if it gets too hot, but you have liquid water and your atmosphere might get a little crazy, like this zinc sulfide atmosphere. If it's too cold, you wouldn't have liquid water. But yeah, that's basically what we're looking for. Is it possible to have liquid water in an atmosphere conducive, similar to Earth, essentially? And we've found so far around 360 planets that exist in what we call the habitable zone. As I said, yeah, so we found potentially habitable worlds in our solar system. This is a very popular system. This is the TRAPPIST-1 system, where they found 7 Earth-sized planets orbiting a dwarf star, which we think there could be liquid water on potentially all of them. So it's possible, maybe, that there is life on these planets, but unfortunately they're very, very, very far away. So I don't think we'll ever visit it in our lifetime. But of course, the habitable zone is just a theory, and of course, it's more complicated than having just water. We have to think about a lot of things when we think about habitability. We need to think about the stellar effects on the planet. How does the planet interact with the star around it? Maybe the star is emitting a lot of high energy radiation that would basically blast away any life on the planet. It's possible that there are interactions gravitationally in the solar system from other planets or other orbiting bodies that would make life inhospitable. For example, you don't want your planet getting flung out of the solar system. That would be bad. And then, of course, as we talked about already, the atmosphere. The atmosphere is very important. There's other planetary properties that are also that we need to keep in mind, like surface properties and interior properties. Does it have a magnetic field around it? That's pretty important. So let's get back to this question. Could there really be so many habitable worlds in a galaxy far, far away? Well, looking at just the numbers, we already mentioned there's probably billions of exoplanets in our galaxy. So sure, why not? There could be just as many habitable worlds, because in Star Wars, they're zipping around at essentially the speed of light. They've got hyperdrive, so they can just travel there. Okay, there is a slight catch though, because we can't travel the speed of light, but even if we could, which I'm not sure that we can, because the laws of physics sort of break down as you approach that speed, our nearest neighbor is about 4 light years away. So traveling at the speed of light, it would still take us 4 years to get there. And in Star Wars, they get there in like the blink of an eye. So it's a little bit of movie magic. Not really. Now, okay, you could say, what if all the planets are really close to each other? Sure, but I don't know if that was the thinking. So yeah, a little bit of movie magic there, but I think it's fun to think about. Although I guess I will say, it's possible maybe also if people in Star Wars could in some way warp space-time. Speaking of warping space-time, I'm going to hand it off to Mugdha now so she can talk about Interstellar. Thank you.
Thank you, Reilly. Can everyone hear me in the back? Yes. Awesome. So, Interstellar, let's get into it. This movie is really special, to me at least, if not to everyone else. It came out in November 2014, and I will tell you in a bit why that is actually important. But this movie, when it came out, it was just so exciting to the movie community because it was just such a great movie. Like, we've seen all these kind of space dramas that evolve like dramas, and then to the astronomy community, it was so exciting because it was such good astronomy representation in a movie. And just some quick facts. Like I said, Interstellar was one of the most scientifically accurate space movies, and part of that reason was because there was an actual physics Nobel laureate, Kip Thorne, that was part of writing the script, producing the movie. So Christopher Nolan, have we seen the Batman movies? Yeah? So Christopher Nolan of the Batman movies directed this and produced this movie, and he sat down with a physicist to write the script. So a lot of the stuff in the movie is actually super realistic, and we'll try to unpack what's realistic and what's just, like Reilly said, movie magic. This movie cost about $700 million, which is crazy, and just again speaks to the popularity of space movies, which is awesome. And I just want to point out that because there was so much realistic physics, they actually had to do a lot of physics simulations. And what that meant was that they generated 800 terabytes of data for this one movie. No real astronomer, I think, is ever going to go through that much data. I think we would be terrified to actually go through that much data. But this movie, they did really high-res simulations, so any kind of real scientific simulation, but in like IMAX quality, Dolby sound, all of that stuff. So it amounted to, they actually had to create technology to keep up with the data for a movie. Wild, right? It's crazy. Alright, so I just want to quickly go through the plot because it's really important to the movie. And again, if anyone hasn't watched it, I really apologize for the spoilers, but it's going to be worth it. So basically there's like this dystopian near future where Earth is kind of dying because of climate change like issues. And NASA is on a secret mission to recruit these 4 astronauts, one of which is Matthew McConaughey. And they're trying to send them to these candidate habitable planets to see if they can basically create a new Earth, because they just believe that this Earth is doomed. Now the key word here is candidate habitable planets. Like Reilly was saying, when we say habitable planets, when we try to find it from here Earth, the max we can do is look for the potential of a decent atmosphere and liquid water, right? But that's not essentially the only ingredients required for at least human-like life to survive, right? So So that's kind of really within the realm of reality in the sense that the astronomers did the work to find these candidates. But then the movie magic part is that these astronomers are sent out to those planets to check them out. As of now, we don't have that technology yet. So speaking of going to planets to check them out, which sounds like an amazing job, how do they do that? So they actually space travel via wormholes. So now this fixes that problem that Reilly was talking about in the Star Wars movie, that even if you travel at the speed of light, you're not going to get there fast enough. So a wormhole is basically like a shortcut in space. So imagine if you were here at point A and you wanted to go to point B. Instead of, going how space in the universe dictates the path of going all the way around, basically what a wormhole is just kind of, it makes a tunnel, a shortcut between that point A and point B so that you can just get there so much faster. Alright, so now this wormhole is represented as a sphere, as a bubble in this movie, which kind of was weird because every time we've seen wormholes in pop culture, it's been like some weird hypnotic spirally portal type of thing, which is not at all what this looks like. But they had an amazing explanation for it. So, what the explanation is that if you, say, wanted to go through this projector, you would enter something that looked like a circle because this projector is in 2 dimensions. But space, in reality, is in 3 dimensions. So a circle in 3 dimensions is a sphere. And this was amazing because nobody had ever portrayed a wormhole in something that was scientifically meaningful. And it's even more amazing because the whole concept of a wormhole is completely theoretical. Like, we don't know of any way that it does naturally exist, and we definitely have found them. And we're not sure if we haven't found them because they don't exist, or because if they do exist, they're ridiculously hard to find. But at this point, it is purely theory. So this is definitely theory, but I really appreciate how they've motivated their theory still by physics and math, which is kind of crazy for a movie. And so fast forward through the movie, the astronauts get to the planets, and this one is, so the planets are named after the astronomers who first got them, okay? So this is called Man's Planet. I like to call it Matt Damon's planet, because Dr. Mann is Matt Damon, so that's how I remember it. But basically, it's an ice world. It has 80% Earth's gravity, has an ammonia-filled atmosphere, and liquid water and clouds. So liquid water and clouds. So the astronomers at dystopian near future NASA did their jobs properly because there was liquid water and clouds. So yay NASA astronomers. And all of these other things kind of checks out with like the diversity of exoplanets that Reilly was talking about. That these are all very realistic properties for an exoplanet to have. I just want to point out a really interesting thing, that these ammonia-filled atmosphere and liquid water clouds is something like what we think Saturn's moon Enceladus has, which is crazy. So it's not just that planets have these Earth-like properties, even moons of planets could have them. And actually, NASA said that Enceladus, the moon of Saturn, is probably their best bet to find life outside of Earth in the most immediate future, because we think that it has these kind of geysers that are bursting out of the surface of this moon, which is so crazy. So it kind of, to astronomers, resembles what the Earth looked like when it was just cooling down and life was beginning to come up. Microorganisms were beginning to show up because we had a lot of geyser and jet activity. So it's kind of cool. Saturn's moon, crazy, right? All right. So next planet is Miller's planet. This planet is a full water world. It had 130% Earth's gravity, meaning you would weigh 30% more on that planet as you weigh on Earth here if you measured in pounds. But meaning that it would be very hard to walk there because you would just feel like you have 30% extra ankle weight on your legs. And it was very close to a black hole, Gargantua, which we will unpack in just a couple of minutes. But before that, I just want to say that planet close to a black hole, we haven't actually found that yet, but Kip Thorne, who was the Nobel laureate who worked on this, actually worked on general relativity. So black holes and relativity was kind of his domain. So he made sure that he found a simulation in which you could potentially have a stable orbit around a black hole. There was a condition, like the black hole had to spin at 99.99999% of the speed of light or something, and he made sure that the movie makers included that in their simulation, and that was the visualization that we actually saw in the movie, which is crazy, so much attention to detail. So in the realm of theoretical physics, that was possible, so that's kind of why this planet was there. And basically what that means is a massive black hole comes with a very, very strong gravitational field. And a very, very strong gravitational field is then responsible for massive tidal waves. The same way that the moon's gravity is responsible for the high tides and low tides on Earth. This is just like that, except with a massive, like a billion, a black hole that has the mass of 1 billion suns. So the tidal waves that came with it were so crazy. So this is a little graphic. The tallest waves recorded on Earth are about 100 feet. You can find them in places like Hawaii, which is notorious for really big waves. Empire State Building at 1,400 feet. And then there's a wave in Interstellar on this planet at 4,000 feet. Just for scale, we have yet on Earth to build something that tall vertically. So again, as we see this common thread of that, yes, this planet does have liquid water, but if you try to live there and you had 4,000-foot waves coming crashing down on you, your bones would not sustain them. So, like we said, liquid water is habitability in astronomy terms, but not really conducive to us living there. And coming to that black hole we're talking about Gargantuan. So this was the still from the movie. This is what the black hole looked like. It again looks nothing like any black hole that any other movie has shown. But it is the most accurate representation of a supermassive black hole that has ever been shown in any kind of pop culture. And before we get into the specifics of why this looks so crazy and amazing, I just want to talk about what is a black hole. So a black hole, contrary to what its name suggests, is not a hole at all. It's quite the opposite. It is a lot of mass compressed into a very, very, very small volume. So basically it is a very, very, very dense object. And the really high density then means that its gravitational pull is so strong that nothing, not even light, can escape from it. So if you imagine the universe as this blue rubber sheet, so if your universe was like a rubber sheet and if you place something heavy on it, like a mass, so if on a rubber sheet you put like a metal ball on it, it's going to create a little dent, a dip in that rubber sheet. So that's kind of what actually happens in the universe, and that dent in the rubber sheet is what we have heard as space-time curvature. So mass literally bends space-time. It leaves an imprint in space-time. So now that's what would look like for a regular mass, regular density object. But now when you have a black hole where all of this mass is concentrated into a very, very, very small volume, that disturbance in space-time is just super, super obvious. It is very, very drastic. And this kind of well-like shape is literally what it's called. It's called a gravitational potential well. And once you cross this part of the potential well, this event horizon, that's where nothing, not even light, can return from it, just because of the intense gravitational field that it has. So black holes are really cool. And this is, well, not this, but black holes are the topic of my PhD dissertation. Alright, so this picture looks very similar to the first still I showed you, but this is actually from a simulation from NASA. So again, I just want to point out that it looks so close and so similar to what was in a movie which blows my mind. And now, again, you're like, this glowing red stuff around the black hole, what? You just told me that a black hole eats everything inside, what's going on? So, it's true that once you cross a certain point around a black hole, there is no return. But not everything immediately gets sucked into a black hole around it, because then nothing would ever exist, right? So this, what actually happens around the black hole, the gas and the space dust that is around it kind of wants to go towards it because it has such a high gravity, but it can't all just fall in randomly. So it kind of goes towards it and just swirls and makes this really big accretion disk, it's called. So it makes a disk around the black hole that slowly falls into the black hole there. And because the gravity of that black hole is so strong, these dust and gas particles are orbiting so fast that they start glowing. They become hot, like how a piece of coal or wood becomes hot when you, it starts glowing red when you make it hot. That's exactly what's happening. This is just glowing stardust. So that's what's happening. And again, this is kind of like, if you would imagine, if you fill the bathtub with water, and then you pull the plug, you pull the stopper, all the water doesn't just immediately disappear, right? The water slowly will swirl around the drain and eventually go down. And that's exactly what's happening with this black hole. Dust and gas is swirling around and slowly going inside. So, if you agree with me, you're like, okay, black hole, disk around it, but what is this weird structure that has disk above and below that looks crazy? So what that actually is, the black hole actually does have one disk, but its gravity is so strong that it literally shows you what's behind the black hole. So it acts like a lens because it is bending and warping space-time so dramatically that you can see what is behind the black hole, which is what this is. This is the image of the backside of the accretion disk of the black hole. It's just shown to you like this, upwards. And the same thing, the image of the lower side of that disk is kind of folded down and shown to you. So it's just one disk, it's just that you're being able to see what's behind it, which is crazy. It's still crazy. And I just wanted to say that that movie was released in November of 2014. We imaged a black hole for the first time ever in, I think, sometime in 2019. So 5 years before we even took a real picture of a black hole, we had such amazing, accurate representation of a black hole in a movie. So crazy. And this, again, was the actual picture. This is what scientists expected the simulation, like in reality, to look like. They blurred it down to the resolution that the telescope could see, and that was the actual picture. Now, a lot of people, when it came out, told me, well, we have so much technology, that doesn't look like much, it looks like a donut. And I'm like, well, of course it does, because this black hole is not of our galaxy, it's of another galaxy super far away. And the equivalent of imaging this black hole in that galaxy is literally the equivalent of putting an orange on the moon and being able to zoom in and see the orange super clearly. Now just think of that thing. That is crazy to have such high resolution from Earth. It took us so many years after knowing the existence of black hole to do that, so that's amazing. Now, you're like, okay, but those two pictures don't look anything alike, so what is this so-called astronomer so excited about? Well, they are the same thing. It's just a matter of orientation. So I said that the black hole has a ring of gas and dust around it, kind of like Saturn has a ring of moons and dust around it, right? So we from Earth are able to see Saturn with its rings cutting across the planet. And that's kind of what they showed in that movie, Interstellar. But in reality, in the particular galaxy that they took a picture of, they happened to see the black hole kind of like a top-down view. So like if you were in a spaceship and you flew above Saturn, what you would see is just like a donut, like the rings around the planet, or in this case, the disk around the black hole. So again, it is the same thing, it's super realistic. These pictures are also from simulations, and it is just a matter of how you view it. Interstellar had a choice in how they viewed it. We don't, because we get what nature gives. But again, super, super realistic. So, okay, now is when the science starts to break down, right? Because then in the movie, he being Matthew McConaughey, goes inside the black hole. Now in the movie, that leads him to kind of like a tesseract where he can physically move between time and space, and all this tesseract is behind his kid's bookshelf. I will tell you that we don't know what's behind a black hole or inside a black hole, but I will 100% give you in writing that it's not a kid's bookshelf. I promise you that. So in reality, although if you were close to a black hole, what would happen is that you would most likely turn into space noodles, spaghetti, and then dust. So this is that famous thing that you may or may not have heard called spaghettification. And you literally will turn to spaghetti. The reason for that though is that, so we show that really deep gravitational well around the black hole. So if you were anywhere close to a black hole, every atom inside your body is attracted to that black hole at vastly different forces because it's changing so rapidly. So your legs and your arms would have different forces pulling towards that black hole, which would literally like make you into a noodle. So no kids' bookshelf behind a black hole, and potentially we wouldn't survive if we were anywhere close to it. Okay, so now the question really is, what is inside a black hole, right? Spoiler alert, no one knows. And some people seem to think that it may be the entrance to a wormhole, where if you go inside a black hole, you'll come out of a doppelganger partner white hole, and it will be like a shortcut through space. Again, complete theory. What it could as well be is this void that Squidward is stumbling into. And again, we don't know if either of those are true, if any of those are true, right? Because we just literally don't know. So now, you might be thinking, okay, Mugdha, but what is really inside a black hole, right? So my answer is probably nothing and everything. And I say nothing is because when you thought, if you were able to keep your mind and body intact if you went inside a black hole, all the laws of physics, relativity, everything we know don't apply at such extreme conditions. So I don't think you would be able to see anything, but if you weren't able to see anything, I don't think you would understand what you were seeing. So which is why I said nothing. I don't know. There's probably nothing in there. Also, time would probably stop for you. It would just be a crazy trip. And I say everything because we said that the definition of a black hole is this immense amount of mass concentrated in this tiny volume, right? So it literally has 1 billion suns at where you are, which is literally almost all the matter that you can imagine. Like, I don't think you can imagine a billion or a million suns worth of matter. So that's why I say nothing and everything. What I think would happen though is that you would just feel like you are in constant free fall. I don't think you would ever get that feeling. So if you, like me, are an adrenaline junkie, love roller coasters, probably black hole is the place to go. So if anyone manages to do it and keeps their mind and body intact, please come back and let me know. I'm very curious. We will do another astronomy attack session for that. But if you, like me, also do not want to turn into space noodles, just stay away from a black hole. And that's it from me. Any questions? Oh, I did forget to say at the end that I went through all of this, but the bottom line is Interstellar is a great movie and you all must watch it, and if and when you do, you should discuss it with all your friends, or if you have any questions, please come to me. I love talking about that movie so much. Yes?
So, do you think that on the other side of the black hole, perhaps like a white hole exists?
Yes, the question was, on the other side of the black hole, would a white hole exist? Yeah, and that is something that has been theorized, like I said, with that wormhole explanation, that people think, Not that. Okay, yeah. This kind of figure, people think that maybe the black hole, nothing ever comes out of it because you're not looking in the right place and it goes out of it for white hole. But again, we have no way of confirming nor denying that. Sounding politician right now, but yeah, we just don't know, you know. Yeah, question. Do wormholes occur naturally? I'm going to say that our knowledge of physics right now is telling us no, that there is no way for such a singularity or shortcut to exist. But I will also say that we are just at the cusp of beginning to understand space-time and gravitational waves. We know that it was, 2017 when we discovered the first gravitational wave incident. Einstein's theories predicted it for a much longer time than that. So maybe in a few years our answer will be different, but as of now we don't think they can actually exist. Yes?
You mentioned exoplanets and other life. What kind of life have you found?
Have we found?
Yeah, or have you found in other habitable planet exoplanets?
Yeah, I will let Reilly answer this question as our exoplanet expert.
So, was the question, what kind of life have we found elsewhere?
Yeah, or how is it habitable?
Right, so we have yet to confirm any life elsewhere, but basically our theory says that there are planets that we've picked out where there may be life, but we'd have to probe more. Some things that we can do are look at the atmospheres of these planets and look for things that we call biosignatures, which is one thing that we hope to do in the near future when we launch JWST. We're going to be able to get more detailed insight into the atmospheres of these planets far away, and we'll be able to see maybe if there's like, what are some common, phosphorus, I think that's one, things like that in the atmospheres of planets.
How common are black holes? Like, if you got a million stars in the sky, there are a million stars, and if I were popping around space at my light year speed, how likely is it that I would run into it and be like, ah, shit?
Yeah, that's a great question. The question was how likely is it to find a black hole out in space? Well, I would say that they are more common than we think they are. One, because, again, as Reilly was saying earlier, almost all the things that we know about space are from light that we can see. And by definition, a black hole, unless it is massive enough to have that kind of a gas disk around it, is not going to be visible. So the thing that we know is that almost every galaxy has one of those supermassive black holes at the center. We have one in the Milky Way as well, which creates bubbles and does all kinds of crazy things. And yes, like, so using the gravitational waves from LIGO, we have found like black holes that are kind of the size and not size, right? The mass of the sun, so smaller things that potentially are dead stars. So I'm going to say that they're quite common. I don't think we have a full grasp on like you asked, for a million stars, how many black holes will that find? I don't think we have a full grasp on that, but I think they're more common than we used to think they are. Thank you. Problem. Yes?
This is maybe a relevant question, but so we can't see planets because they don't glow. We can see stars because they emit light. Then why do our planets look like stars?
Okay, so the question was, getting back to planets don't shine like stars do. Why do our planets look like stars? Right. That's because it's reflecting light from the sun. Yeah. That is to say, planets do glow, just not the same way that stars do. They glow in just different wavelengths, so like you could imagine like infrared. But we can't really see that with our eyes. And yeah, so yeah, they don't shine like stars. They don't fuse. That's the key. But
Also, the key is that our celestial planets are super close to us, of course, because we have these planets are like way out. Any other questions? Yes.
Just kind of on the talk of exoplanets and looking for life kind of beyond Earth, how do you kind of determine that you found life? Are you still looking for water and oxygen, or still looking for carbon-based life, or what are you looking for?
That's a great question. Well, right. So basically, the question is, when you're looking for life elsewhere, what kind of life are you looking for, and how do you determine that you found it? And I'd say the most definitive way that we would be able to determine if we found life is if we could actually visit these places. But unfortunately, that's not really possible. So we have to. I think the closest that we can come to actually confirming any sort of life is looking at the sort of chemistry of these planets, and seeing based on light we can determine certain elements, because certain elements emit and absorb light at certain wavelengths, and so then we can look at a spectrum of a star and a planet, or rather the spectrum of an atmosphere, and determine what it's made of. And I guess what we would have to do is look for organic compounds, and that would, unfortunately, it wouldn't be a total confirmation, but it'd be closest thing I think we can get. Yeah.